Hello my dear students, this is Akash SD and welcome to the SD physics classes. I hope so you all are doing really great. So students, in this video we are going to learn everything about the conductors, like how the electric field will be on the surface of the conductor, and what about the electric potential on the surface of the conductor, inside the conductor, all around it. We are going to see in this video. That means this video is going to be the complete package of the properties and characteristics of the conductors. Okay, and at the end of the video we will see the dielectric also, like how the dielectric will behave if we will put it inside the external electric field. Okay students, so let's start the video and let's learn all these things. So here you can see very well. First thing we are going to see earthing a conductor, because we have learned everything, means number of times in our homes also we will talk about the earthing and all that. But what is the actual meaning of the earthing? Okay, so let's go through it. Earth is a good conductor of electricity, okay, and for most practical purpose its potential is assumed to be zero. Again I am telling you here, for the practical purpose what is there, its potential is the assumed to be zero. Actually it is not zero, little bit 0.1, 0.01 like this, but we used to consider zero here. Okay, now next one see again. A conductor is said to be earthed or grounded whenever it is connected to the earth. Now that means earthing word is coming from when the conductor is connected to earth or ground. Okay, next one. In that case its potential becomes zero, as we have seen before also. Now after that here, the charge will flow from conductor to earth or from earth to conductor to make its potential zero. Okay, remember that here charge means electrons. That means when the conductor is the negative charge and we are connecting it to the ground, then what will happen, that electron will flow into the ground. Similarly, if any conductor is positive charge and we are connecting it to the ground, then what will happen, that electron will come from the earth and it will go into the conductor and it will make the potential zero. Okay, so here charge means what? Here the charge means the electrons, maybe conductor to the earth, maybe earth to the conductor. Okay students, so this is about the earthing a conductor. Next one, let's see what is the meaning of equipotential surfaces. Now even the name is telling equipotential, that means the potential on the surface will be what? Same. That's why the name is the equi. So let's see, any surface over which the electric potential is same everywhere is called an equipotential surface. Now electric potential is same, very easy. Now these points we have to remember that, because in exam they used to ask the question from these points. Okay, so see here please, first one, angle between electric field lines and its equipotential surface is always 90 degree. Later we will see the diagram also, no problem here, but remember that here angle between electric field lines and its equipotential surface how much? 90 degree. That means we can tell electric field lines are perpendicular to the equipotential surface because angle how much? 90 degree. Next one, see, potential difference between any two points in an equipotential surface is always zero. Anyhow potential at all the points is same, so potential difference how much? Zero. And the last one, see, work done by external force to move charge on equipotential surface is always how much? 0 degree. How can we tell here? Because here I have taught you work done by the external force to move a charge from A to B is given by Q into what is this? VB minus VA. This basics we know. What happens? Potential difference on the equipotential surface how much? 0. So as this difference how much? 0. That's why what will happen that here, work done by the external force to move any charge on the equipotential surface how much? 0. Okay, so please remember that these 3 points very very important. Okay, great. Now students, let's see next one. Now we are going to draw equipotential surfaces for different kinds of charge distribution. Okay, so let's see one by one. So what is given here? See, first one, the equipotential surface are a family of concentric spheres for a point charge or a sphere of charge as shown in diagram here. Na? So first what we are going to see? We are going to see for the point charge. So let's say for example here I have taken one charge, I have taken here for example what is there? Q charge is there. Okay, so now what will happen that here in this situation, students see, here it will be the what? Family of the spheres. Now so see here please, here see one sphere I have drawn here, this one. Next one see I have drawn here, this one. and here also I have drawn here this one. So what is the students here? Here you can see this is the point charge Q, but what is this? This is the equipotential surfaces are there, because you know very well what is the formula of the potential. The formula of the potential is 1 by 4 pi epsilon naught into Q by R. That means what is this? V is inversely proportional to R. And you know very well here from the charge, this all radius is constant here, please, this radius, even R1, R2, and even this one, R3. So what is there? This first sphere is equidistant from the charge. So equipotential surface, all the points at the same potential V1. Okay, similarly next one, this points on the sphere also equidistant, that means here V2, and here also how much here? V3, like this. So what will happen that here? They are which one? Equipotential surfaces are there. Even this is for the point charge. Even we can take for the any spherical configuration also. Let's take for example here. No? Here one sphere is there and here some charge is there like this. Okay. Here also. Symmetrical charge distribution will be there. Then what will happen that here in this situation? Here also which kind of equipotential surface? Same, spherical. See here. Again see, I'll draw here. No? See. Like this. Okay, they are also water. They are also students equipotential surfaces are here. Okay, and I can give the names. Let's take V1, V2, V3, and this sphere will come at the center somewhat. Okay, so for the point charge also, and for the what is there? Sphere of charge. What will happen? Which kind of equipotential surface will be there? Spherical, concentric spheres. Okay, again I'm telling you, this is the isolated. This is also isolated, not two charges and all that. Okay, great. Next students, let's see. Second one, the equipotential surface are a family of concentric cylinders for a line of charge or a cylinder of charge as shown in diagram is there. Okay, so now what I will take here? Here I will take here this line I have taken here. Okay, and what will happen that here in this situation, what kind of equipotential surface will be there? Just like a cylindrical one here. Okay, like this, cylinders here. Okay. And here charge is there. Okay, what is there? The charge is here. Everywhere charge is there. Okay, like this, no? And here we can draw one more like this. See, like this here. Cylinders will be there. No, like this we can draw here. No, and let me take one more here like this. No, like this we can draw here the cylinders here. Now like this here, somewhat. No, so what is there here? Whenever the line charge will be there, which kind is there? The concentric cylinders are there. Even you can draw this also. One more here. Even if you are taking here, one like this kind of is there. Okay, and here everywhere charge is there. No, charge is there. Let's take non-conducting. No, non-conducting I have taken. So here also what will happen is students here in this section also we can draw here just like a cylinders are here. Okay, like this. Concentric cylinders are there. Okay, like this. You can draw here, I am drawing only 2 or 3, but we can draw multiple is there. Okay, so please remember that this thing. Okay students, great. Line charge is there, line charge. Next one, let's see, next one. Third one, for uniform electric field lines, very important for the competitive exam, plane equipotential surfaces are as shown in diagram is there. Now what I am going to do here, I am going to draw here the uniform electric field. How to draw the uniform electric field? Like this here, see, let's take. Now this is what? This is the uniform electric field. Let's take for example, this electric field is along x direction. Which direction? X direction. Now what will happen that here in this situation, if I will draw here the equipotential surface, it will be something like this is there. Okay, like this. Okay, what is they are? They are the plane equipotential surface like this is there. Okay, and one thing please remember that here, this is in a which plane? This is in a which plane here? This is in a YZ plane. Perpendicular. What I have told you? I have told you angle between electric field lines and its equipotential surface how much? 90 degrees. So electric field along x direction. But equipotential surface in which plane? YZ plane. That means they are making how much angle? 90 degree. Even in the previous situations also. Here also what will happen that here if I will draw now, if I will draw here, see, electric field lines will be something like this. Okay. So here also what will happen that here they will make how much angle? They will make here angle 90 degree. This is the electric field. This side also we can draw actually. See here. 90 degrees there. Okay, this is the water, this is the electric field is there. Even we can draw before also. Here also if I draw the electric field lines, it will go like this here. This is the electric field lines is there. Okay, like this. Positive charge, no? So like this here. No, like this. Always. What is this? This white color is water, electric field lines. Electric field lines. How much angle is there? See, here angle how much? 90 degree. Even we can draw here also. No? Okay, we'll just do here. See, it is not going that much symmetrical, but please, I hope so you are understanding what I mean to tell here. Okay, like this. How much angle? 90 degree. And if in case this is the conductor, you will see that electric field inside the conductor will be always how much? 0, and it will be equipotential surface inside and on the surface also. We are going to learn all these things. Okay, students. So all these things we have seen that. No, all these things. Next one, see. Fourth one. Equipotential surface for two positive and equal charges are as shown in diagram is there. Okay, students. So what I will do here? I will take here the positive charges are there. Let's take for example here, no, and positive charges I have taken here, no, here plus Q, and here also how much here? Plus Q is there. Okay, then how to draw here the? See here please. Here students, it will be not a symmetrical space, somewhat unsymmetrical. What will be there? It will be somewhat inward actually. See, let me draw here please like this, like this, like this. Okay, here also we can draw here somewhat like this, like this. Somewhat shifting inward, no? Inward it will be shifting somewhat is there, no? If we can draw here like this also. Okay, and one line we can draw like this also. See, like this, no? Not corner like this here. Okay, somewhat more or less. What is this? This is the equipotential surface for water for the two positive charges are there. Okay, for two positive charges. Next one is students, if I take here dipole, you know very well what is the meaning of the dipole students. What is the meaning of the dipole? Dipole means, see here I have taken here, no, dipole how to get here, see, this is minus Q and this is how much here? Plus Q. Here also what will be there? Here also, see here please. One line will be there, you know very well about the dipole, now on the equatorial point, see, this one here. This is also equipotential surface just in the middle. Okay, and here potential will be how much here? This will be 0. Okay, just 1 minute. This will be 0, 0. And after that, how to draw the equipotential surfaces students here? See here, please. Here it will be something unsymmetrical is there. Now it will be outward somewhat, this side. Like this here. See, this all lines will match up. This all lines. Okay, here also see, like this. Like this it will go here. Okay, so more or less it will be water. Equipotential surfaces are there. Okay, this sphere will shift somewhat outward, but previous one it will shift somewhat inward. I hope so you are understanding what I am telling here. Okay, students. So please remember that this one and this one both will be water symmetrical. Okay, great. Next one, students. Now we have come to the electrostatics of conductors. Electrostatics of conductors. Here, please. Here. Now, what is this? See. Conductors are materials which contain large number of free electrons which can move freely inside the conductor. Okay, and second one, let's say here, electric field lines never exist within the conductors. Why? Because electric field intensity inside it always how much? 0. Even we have done before also. Okay, third one, see, charge always resides on the outer surface of the conductor. If the conductor means charge will be where? Always on the surface. Any shape of the conductor is no problem. And see here, conductors are always what? Equipotential surfaces. Conductors are what? Always equipotential surfaces. There are whatever potential on the surface, same potential inside also. Okay, great. Now, students, so all these things we have seen the equipotential surfaces there. Now, see here please. Here what I am going to do here, see. For example, I have taken here one conductor. Let's take here I have taken one conductor is there now, and what is there? Here it is having charge. It is having charge. Can you tell me which kind of charge distribution? Here the charge distribution will be uniform. Why? Because this V will be equipotential. V will be what? Constant. Let's take for example, this radius is R. Okay, so you know what is the potential formula? V equal to K into let's take for example, charge is Q. So K into Q by R. Okay, now students see, now V equal to K by R, you know very well, surface charge density sigma is given by charge by area 4 pi R square. On the conductor always surface charge density because charge will be where? On the surface. So Q how much? Q can be write here what is? Sigma into 4 pi R square. Then what we can write here? V equal to, we can tell very well what will happen that here, this R and this R cancelled out. That means we can write here K into sigma into 4 pi into R, or if I write here sigma into R is equal to V by K into sigma into 4 pi. Can you check out here? Now sigma into R, V by K into sigma into, oh no, sigma will, because sigma already is there, na? Okay, 1 minute here. This sigma will not be there, this sigma. Okay, now okay. Now check out sigma into R, how much here? V by K into 4 pi. That means all these things are what? Constant. That means we can tell here, students, this sigma into R will be what? Constant. This is having very special meaning. What is the meaning? The meaning is that if in case a regular shape conductor is there, which conductor? Regular shape, like a sphere is there, it is a regular shape. So here what will happen that here in this situation, R is constant. See, for all the distances, what is there? R is constant. Even I can tell this also, see, sigma is inversely proportional to R. So what will happen that here? Everywhere what is there? R is constant. That means for regular shape conductor, what will be there? The sigma will be constant because R is constant. But if in case irregular shape conductor is there, which one? Irregular shape. Irregular shape. Then what is there? This is valid here. Sigma inversely proportional to R. What is the meaning of this, students? Just let me see here, please. Here. See, here I am going to draw here the irregular shape. Which one? Irregular. Irregular shape. So let's take for example, it is given like this. No? So conductor, regular, irregular, irregular. So here what will be there? Where the radius of curvature is less. Radius of curvature is less. What I am telling, where the radius of curvature is less, sigma will be what? More. That means here, when we are going in this direction, R is keep on decreasing, your sigma will keep on increase. So here, please, here somewhat far distance, but here it will be go very close, very close. Here more and more. Then again it will keep on increase here. Okay. So where sigma is maximum? Where sigma is maximum? Sigma is maximum here. Sigma max. Now because one corner is there, wherever the corners, sigma will be maximum because the radius of curvature will be very, very small. So this is for regular shape. This is for which one? Irregular. Again I am writing here. This is irregular. This is what? Irregular. This is irregular. Here sigma constant. Here sigma variable. Okay. Here sigma variable. Here sigma variable. Here sigma constant. This one. Okay. And here sigma variable. Okay. Very easy, very easy. Okay, next one. Let's see now. Next one. Now, note. As I have told you, whatever I have told you now, here please see. Surface charge density is always uniform on a regular shaped conductor, but non-uniform on a irregular shaped conductor, as I have told you. Okay, next one. See. Electric field lines are always perpendicular to equipotential surfaces. That also I have told you. Next one. When a conductor is grounded, its potential becomes 0. Okay. And last one here. Electric field intensity near a conducting surface is given by here. No? Near a conducting surface is given by here. So here what will happen that here, remember that here, for example here, some conductor is there like this. Okay. So what will happen that, let's take for example here I have taken point A, here I have taken point B, here I have taken point C. So at all the points what will happen that here, equal to sigma by epsilon naught. Okay, sigma by epsilon naught will be there. Here you have to take sigma A by epsilon naught. Here sigma B by epsilon naught. Here sigma C by epsilon naught. Okay. So as the sigma will be different. So what will happen? Electric field will be different value for irregular shape conductor. Okay. Regular means everywhere sigma same. So electric field lines will be also same. Okay. Great. Now students, next one please see. Charge distribution on conductors. Now, this is the somewhat little bit tough topic, but okay, we'll see. The charge distribution on surface of conductor. So what is there? Let's take for example, one conductor is there like this. Where will be charge? The charge will be on the surface always. Even conductor is solid, hollow, does not matter, always on the surface. But now what I am going to do here, next one here please. Here, the same thing, first one, but I have made it a grounded. What I have done here, I have made it a grounded. Now, so what is there here? See, this one is there. See, this is there. Now, the moment what will do here? The moment will connect to the ground here. No, this is the grounding symbol. No, ground. So what will happen that here? You know very well, V equal to K into Q by R. Okay, here Q is there. So the moment will make it grounded here, V will be how much here? 0. So the moment V is 0, what will happen? Q will be 0. That means when isolated conductor is there and we are connecting it to the ground, then what will happen? All the charge will go into the ground And as I have told you very well, if in case negative charge, that means electrons will go to the ground. If in case positive charge, electrons will come from ground to the conductor here. This is for which one? This is for isolated. Which one again I'm telling you? Isolated. 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 Okay, great. Next one's here. 12th. See here, second one. Now what is happening that here in this situation, students, just let me see here. See here I have taken like this. Here I have taken, and just let me change the color now, and see here also I have taken like this. Now we have the two conductors, and what we have done here, we have given some charge. Let's take here I have given charge Q1, and here I have given charge Q2. So remember that here one basics are there. I will tell you from the Gauss law, close integration. What is there? E dot ds is equal to charge enclosed by epsilon naught. What I have told you, electric field inside the conductor is always 0. So E will be 0. So when E will be 0, what about the charge enclosed? Charge enclosed will be also 0. Whatever distribution of charge will happen on the conductor, it will happen to make electric field inside the conductor always how much? 0. So the moment we'll give this charge Q1 and Q2, you know what will happen? That redistribution of charge will happen. What will happen? ROC means what? Redistribution of charge. And you know very well, when the redistribution of charge will happen, just let me draw here. This is here. No, just let me draw here. No. Redistribution of charge, no, same I have drawn here. So after the redistribution of charge, what will happen that here, facing surfaces will have equal and opposite charge. That means here how much charge? Q1. Here how much charge? Minus Q1. Here see. This surface and this surface facing. So here Q1 and here minus Q1. But from the conservation of charge, here total charge how much? Q2. So here should be outer how much? Total Q2. That means here it will be how much here? Q1 plus Q2. So now you see, before redistribution, total charge on this conductor how much? Q1. Here also how much? Q1. This is where outer surface. Inner surface is 0. Inner surface is 0. Outer only Q1. And before the redistribution, here total charge how much? Q2. Here how much? Minus Q1 plus Q1 plus Q2. Q1 cancel. How much? Q2. So conservation of charge will be valid, but why this redistribution of charge is happening? So that electric field inside the conductor should be how much? Electric field inside the conductor should be how much? 0. So only this redistribution is taken place. So only this redistribution has taken place. Okay. Now students, for the same thing, second, I will do the grounding is there. Let's take for example is there. Now grounding. Grounding also let me tell you. Let's take for example here. Just 1 minute. It should look somewhat similar at least. Okay. And here let me take here the radius. This one R1 and this one R2. Okay. And let's take here I have taken charge Q1. Okay. And what we have done here, we have connected to the ground here. Okay. We have connected to the ground now. And let's take here in this situation charge how much? X. So what I will do here, students, here please here. First I will take here one point is there. I have taken point A. So potential at point A how much here? Due to the first one, VA due to first one plus VA due to second one. Okay. Now students see, point A with respect to 1. Point A, this one with respect to 1. This is first one. This is second one. So point A with respect to 1 is where? Outside. Where? Outside. And point A with respect to 2 where? On the surface. Where? On the surface. S means surface. So now outside means what we write here? K into actual distance. K into Q by R2. This actual distance R2 plus K into X by R2 on the surface. And when we will connect to the ground, potential will become how much? 0. So when you will simplify this, you know what will come? It will come X equal to minus Q. What is coming? X equal to minus Q. That means what will happen? The minus Q charge will be there on the conductor. What I have told you, isolated means total charge will go into the ground. But whenever multiple conductors are there, it is grounded, potential is 0, but charge will not be 0. What will happen there? Minus Q charge will be there. Depending upon the making the electric field 0, charge may be on the outer surface, maybe inner surface. But in this situation, later when you will just think that this minus Q1 charge will come on the inner surface of the outer conductor is there. Okay, great. So here what we have done, we have connected to which one? Outer one grounded. Now what I will do here, in this thing, little bit, I will do the changes here. See, little bit I have done the changes here. See, okay. So see. Now what will happen at here? Next one, let's take here. See here. Now what I have done, students, here in this situation, let's take here I have taken charge 1 minute, see, here charge is Q and here X and here I have connected to the ground now. Okay, and now what I will do here, I will take the point where, I will take the point on the inner surface is there. Okay, just let me take here, the point is here. Let's take, I have taken point B is here. Okay, now students, just 1 minute, let me rough all this now. So now what I am going to do here, I am going to calculate the potential where, I am going to calculate the potential here at point B. So see here, potential at point B, that means VB1 plus VB2. Now tell me please here, B with respect to 1 where? B with respect to 1 is where? On the surface. And B with respect to 2? B with respect to 2, outer one is the 2 here. What I am telling, outer one is the 2. Outer one is the 2. So B with respect to 2 where? Inside. Inside. Okay. Now what will happen at here? At the surface means which one? Same distance here. So what we write here? K into X by R1. See here please, for this one here. For this one here, how much charge is X? Distance how much? R1. So K into X by R1 plus K into Q by whatever potential on the surface, say potential where? Inside. That means KQ by R2. And as it is connected to the ground, inner one is connected to the ground. Here potential how much? 0. That means here 0. Now again we have to simplify this. Simplify and tell me please. See. So 0 equal to K. And here what will happen at here? See. X by R1 plus Q by R2. This is very important for the capacitor. Then after that I will write here. What will happen at here? See. X by R1 equal to minus Q by R2. X by R1 is equal to minus Q by R2. Then what X will come? X will come here minus Q R1 by R2. Okay. This charge will come when we are connecting inner one to the ground. Inner one to the ground. Okay. So both these things we have done here. Okay. Great. Now students, we will come to this one here. Very easy. See here. Effect of metallic slab between two charge plates is there. Okay. So just let me take here. I have taken here the two charge plates. This is one charge plate. Let it be somewhat straight. No. Okay, no problem is there. Now this charge plate I have taken is there. Okay. And let's take. No, let's take here. This one is positive charge. No. Sigma. And let's take this is a negative charge is there. Okay. And here let's take what is there? Minus sigma. You know, electric field will be which direction to which direction? Always positive to negative. That means what is this? This is the external electric field. I have written here E0. Okay, in this direction. Now after that, what I will do here? See here please. Here I am going to take. See, here I have taken here one metallic slab is there. So you know very well, the moment I will take here metallic slab, what will happen there? In this positive will attract the electrons. That means here negative will come. Electrons will move from right side to left side here. So where right side to left side. Here deficiency of electrons, that means positive will come here. Okay, what will come? Positive will come. Now students, what will happen? Because of this inside this metallic slab, one electric field will come in which direction? Positive to negative in this direction. In this direction, E induced. Okay, so what will happen here? External this side, induced this side. That means if I write here the net electric field. So net electric field, how much we can write here? E0 plus E induced. How much? E0 plus E induced. E0 how much? You know very well. As the inside the conductor electric field, how much? 0. That means magnitude wise both will be same. I can write here see E, no, let's take here E, E0 I cap plus this E induced magnitude wise same E, but direction, which direction? Opposite. That means net electric field. Net electric field inside the metallic slab, how much? 0. That means external electric field is cancelled by induced electric field in metallic slab. Please remember that here. Whenever any metallic slab, what will happen? Electric field inside will be how much? 0. Okay. Now students here please here. Now the last one. Effect of dielectric slab between two charge plates is there. Okay. Now what I will do here? Again, let me take here the plates. No problem. I will take here the plates like this. Now this is one plate. And let's take this is also one plate is there. Now here again, students here, this is the positive. What is this? A positive. And here what is this? A negative. Negative. Minus sigma. Now what I am going to do here, students here, what I am going to do here, again I am going to take now one dielectric slab. Which slab? Dielectric slab, not a conductor. Dielectric slab is there. So what happens that in case of conductors, free electrons are there, they will move. But in a dielectric there is no free electrons. Only what will happen? Whatever atoms are there, electrons are revolving around the atoms, that will just shift. That means electrons will shift towards this side here. So here what will happen, that you know what will happen? Here the dipoles will create. What will create, students, here? Dipoles will create like this. Not electron movement, what will happen? The dipoles will create here. So when the dipoles will create, you know what will happen? This side all minus. Okay, all minus. And after that, what will happen that here? If I take one more, see this side plus. Okay, this all plus will be there, plus. So because of that, what happens, students, here please, this external electric field is this side, E naught. But induced electric field will come in which direction? Opposite direction, like this here, because of the induced dipole. And here, you know, interestingly, what will happen that here, if I write here the net electric field, what will happen that here, if I write here, this is E naught plus E induced. So here what will happen that, students, here please, this is E naught I cap, but here what will happen, it will not cancel out completely, okay. That means here we can write here E induced, okay, minus I cap, okay, or we can write here, see, E naught minus E in I cap is there. That means anyhow what will happen, the electric field value will decrease. So when the electric field value will decrease here, we can write here what, E naught by K I cap. Anyhow it will decrease now, so we'll write here E naught by K I cap, okay. And please, if I write here some points, here please, first one, if in case this is vacuum or air, what is there? Air or vacuum. In case of air or vacuum, value of K, how much? 1. Now, if in case instead of this only air is there, so what will happen? The net electric field, nothing is there. That means we can write here only this, E naught I cap. Okay. Second one, students, let's here please here. If I write here the dielectric slab, what is there? Dielectric slab. Dielectric slab value will be how much here? K greater than 1. In this situation, what will happen that here, this E net will be less than E naught value. Less than, na, because K value is greater than 1. And if in case, students, one more thing is there, if in case metallic slab is there, which slab? Metallic slab. K how much? Infinite. That means in this situation, this net electric field value will be how much? 0. Okay, students, so in this video, what we have done, the video is somewhat long, but in this video, we have learned everything about the electrostatics of the conductor. I hope so you have understood very well. Keep studying, keep growing.